Hello everybody, thank you for joining me for my presentation. Today I'll be presenting control software for a flight simulator experience. This was my final year project. Before we begin, I'd like to give a little bit of context about what motion platforms are. Motion platforms is pretty much what it says on the tin. You have a platform over here with usually 6 muscles attached to a fixed base which move the user around. So, yes, what this project primarily aims to do is to write software that connects a commercial flight simulator like X-Plane or Microsoft Flight Simulator to the a wheelchair accessible flight motion platform. It's a version of the previous platform, which was the MDX roller coaster. And because it's a bit different, there's some extra things that it has to account for, like whether the wheelchair is properly docked so it doesn't fall off, or that the winch that pulls it is in safe state. Has to account for that, and also racing it a little bit so it doesn't quite hit the ground. But anyways, the whole point is gets motion from the airplane that the user is controlling, so that so I'm in the user, I'm controlling the airplane. If I pitch up, the platform pitches up, and if I move to the side, moves to the side. It's made to provide a more immersive experience. Yes, something I should mention. The muscles that it uses, they're just hollow tubes. When you put air pressure into them, they contract. It's open loop. That means there's no position feedback, which means that the computer just sets a pressure that it thinks, that it believes that if it sets at this pressure, it's going to contract by this distance and therefore achieve the desired pose. So let's keep going. Key milestones. So the key milestones of this project is basic UI, so the operator will be able to open up a GUI, say start simulation. It starts a simulation, so if connects to X-Plane, the airplane moves around and moves around. It pauses simulation, so the platform stops, but X-Plane does, or maybe it doesn't. And stop just goes back to its stop state, and it doesn't do anything until it goes back to be ready. It's a bit like a microwave, really, where you have different settings. It also aims to calibrate the muscles, which is so that the accuracy of the muscles is within plus or minus 25 millimeters. I'll go into much more detail in that, into the actual muscle calibration. And the software takes into account the wheelchair safe state. I mentioned that before. But yes, full requirements in appendix. So introduction. In short, take the original MDX roller coaster platform, write software that turns it into an MDX flight motion platform. Yes, and as you see, you have the user over there. He's controlling the simulation. He's got a VR or maybe a widescreen monitor, whatever. And as he's sat in there, he enjoys the simulation. So here's a bit of the working software. Should be okay. So you have the airplane in there. Inside. Just down. And that's the video. So yes, software functionality. It works like a state machine, so the software can only do a certain amount, a given set of instructions at any time. So idle state, it does nothing, does nothing, does nothing. User says, all right, you may go into the ready state. Okay, I'm waiting, I'm waiting, I'm waiting. Go into the running state. Okay, I'm reading the motion data from the simulator, from X-Plane. I'm outputting it to the chair. Then in stop state, does nothing, goes back, and that's more or less how it works. It's pretty much like a microwave. It can only either be heating food or it cannot be heating food. This is the sort of software approach, and it works. There's not much else to say. That's the logic. Now, onto the fairly major part that took literally half this project's time span was the muscle calibration. Now, the new platform is bigger. It has bigger muscles that are wider and that they need to be calibrated. Calibration, all it really means is you have this rig over here, you set the muscle to a pressure. You set it to a pressure, you record the distance that it moved. You set it to another pressure, so 100 millibar, 200 millibar, 300 millibar, like that up until 6 bar, and then you do the same going down. You record all of that, and you get sort of two curves going up and going down. You do that for several cycles to get an average, and then you do that for different loads to obtain different curves. And all the end game of all this really is just to ensure that the software knows that, right, for this given payload, I need to set these given pressures for each muscle for it to achieve my desired pose. Because for each desired pose, each actuator has to be a given distance. So that's really the end game of this muscle calibration rig. Yes, so I have in the appendix, I have showing individual curves. These are the 4 curves for the 4 tested loads, which are 13 kilograms, 24 kilograms, 32 kilograms, and 44 kilograms. They're all shown here together. So if you focus here, your attention here, there's this black curve. That is 44 kilograms. So when it goes up, sets this pressure. For this pressure, it's going to be at this distance. For this pressure, it's going to be at this distance. For this pressure, it's going to be at this distance when it goes up. This upper curve over here, and that's the 24. That is the curve going down. So if it's going down, you need to set. If you set to this pressure, you get this distance. If you set this pressure, you get this distance, and like that. These straight lines, they're just a sanity check to check that the load is constant. So right here, the straight line for 44 it's not 44 actually, it's 13. This one 44 kilogram. For 44 kilograms, it's straight. That means great, our load is constant, good. And the same for the rest of the loads. Yes, now there was some evaluation tests done for the pressure to distance, but the one I like to focus on is the distance to pressure evaluation, which at the end of the day says, right, after doing all those tests, how accurate is my system? If I tell my system, right, move this muscle to this distance, am I actually gonna get that distance? And if not, what's the error between? So I tested it with different increments. So the software would say, right, move to 5 millimeters, move to 10 millimeters, 5 millimeter increments, 3 millimeter increments, and 1 millimeter increment. At 5 millimeter increments, it had the least error between the measured and the actual distance, which was just 8 millimeters, so about that big. The biggest was at 3 millimeters, interestingly enough, which was 18 millimeters. Still fairly inaccurate, but it still falls within the 25 millimeter gap that we've set to us. So overall, fairly decent results, but I'd say for future work, it would be to improve the overall accuracy of the system.
2 minutes left.
Excellent. Now, conclusion of future work. In conclusion, the project managed to meet all the major milestones it set out to do. It said, right, I gave the user a basic UI to control the platform. It's, again, within the appendix, and failing that, it's within my reporting, even more excruciating detail. It manages to control the muscles within the 25 millimeter tolerance, and it takes into account the safe state. At the moment, despite the hardware signal not being implemented, because the platform as of now, it's not built. The Witcher accessible version that you saw with the render, it's not built. But it does take this safe state into account as just a signal. And that signal is a Boolean. 1, okay, the platform's fine. 0, it's not fine. Stop what I'm doing. And yes, again, tables and detailing the requirements are in the appendix. The majority of future work could only be implemented when the actual platform was finished built because of the agile methodology. Agile is that the requirements are not set, they were kind of evolved over time, and different bits were being worked on in parallel, as you may have seen in previous presentations where somebody was working on the docking system, somebody was working on the flight stick. Joystick, thank you. And yeah, fully implemented manual control, those are just like the smaller quality of life improvements that I can go into much more detail. And overall, yes. Thank you for listening. I hope you enjoyed my presentation.
I agree. Who's the second marker on this?
I am.
Do you want to start or should I?
So,
Go ahead.
Just to clarify, I mean, I've seen experiments done in the past on the air muscles. What have you done differently to what's been done in the past here?
Excellent question. Let me see if I can find evidence of the previous work. Right here, all right. So, In a previous project, it used laser rangefinders attached to the platform to measure the contraction distance. Now, what I do is I use an encoder. Laser rangefinders are very noisy. As you see right here, this is the difference between the maximum and minimum readings over a given time. So if it's reading 5 millimeters, it's reading 5 millimeters, 49 millimeters, it's kind of all over the place and it takes an average. Mine, nothing. If it reads 10 millimeters, it reads 10 millimeters in one snapshot, 500 snapshots. And so that's kind of what I've done differently, whereas before they just kind of attached laser rangefinders on the actual platform and kind of measured everything at once. I had a dedicated rig, which I've shown before. Not sure if I should.
And did you design the rig?
The rig was pre-made, but originally it was meant to be vertical. We found that because when it was horizontal, originally it was meant to be horizontal. Because it was horizontal and it used a pulley, the measured load was all over the place, so we had to just put it vertically so it stayed constant. Yes, I hope that answers the question.
Okay, go on, Michael.
You mentioned a tolerance requirement of 25 millimeters. Remind me where that came from, because I don't recall that number.
That came from the very beginning, week one, when I was setting the requirements, and
Did you set that, or was it set in the brief? And if you set it, what was the basis for the decision to set 25 millimeters as a target?
I said it because it wasn't declared anywhere in the brief, but I figured since the beginning that I wanted my system to be within a given accuracy. Now, I knew that the muscles could contract up to 2,500 millimeters. And so I said, right, can I at least get the 10% accuracy of that? At least. So that's where they came from.
Okay, so given the experience, what do you think, and you mentioned one of the goals for future work would be to improve the accuracy.
Yes.
What do you think would be the kind of accuracy that you'd like to go for if you were doing future work on this?
If I were doing future work, there should be a short in here somewhere.
Yeah, you mentioned there was a bullet point in the slide saying that one of the actions was improve the accuracy. I'm just wondering, how accurate do you think you'd like to make it? And then the supplemental question is, and what do you think you would do in order to get it more accurate?
When doing the pressure to distance, I found out that the maximum range was like 6 millimeters, but when doing distance to pressure, it increased, the best increased to 8. So my target would be to get it below 6 millimeters, below 6 millimeters of error from the distance to pressure.
And did you give any thought to what you might do in order to get the system to be more accurate?
Yes. First thing, doubling the calibrated loads. So it had, instead of having 4 sets of curves, it has 8. Because it does linear interpolation, and linear interpolation inherently leads to a bit of inaccuracy. So doubling the calibrated loads, the system that I wrote already can handle multiple anyways. And also just really troubleshooting the code, making sure that I'm getting the correct pressure for a correct distance, because sometimes you might, because of how the table lookup works, you might be saying, right, I want 6 millimeters, but it's actually setting the pressure for 5. So really troubleshooting the code, a combination of troubleshooting the code and finding more data.
Okay, are we out of time?
Yeah.
Okay.
Thank you.
Okay, so we've managed to catch up because the next student is not presenting. So we have a break now until 12:15, which is just short of 15 minutes.